דברים ביחס ל-n ולא עם האחרונה, לא תהיה רלוונטיה. אז למה רוצה
לא, אבל בדרך כלל לפני שאנחנו נדבר שם פתאום על הביטוי של הביטוי אחד I want to be in the second row, but I want to be close as usual. לא, אבל הוא לא הולך. טוב, אחרי זה תגיד, אני אראה עשיתי. באמת, מה שאנחנו, כל העניין הזה של להצליח, זה קטע שתפקיד באמת לעשות אותו זהירות, כן, כאילו, זה דורש קצת אינטואיציה.
שמים הבעיה בקורסים האלה, כי אנחנו שלום בפיזיקה.
פיזיקאים עושים את זה עודים למסמית בכלל, מזניחים לך מה שהם צריכים כדי להגיע לפתרון. זה מה שקרה גם פה עכשיו. פיזיקאים בכלל לא מסתכלים על זה, הם אומרים אני צריך להגיע מנקודה א' לנקודה ב', בואו נזניח את כל מה שיביא אותי לשם, אחרי זה ננסה להסביר את זה, כל מיני דברים כאלה. זה בדרך כלל סטודיות רגיל, אני לא רואה בסדר עם זה. אנחנו הולכים לעבור, כל הזה הולך להיות על EM. על Expected Maximization Algorithm. Okay. Hi everyone. So first of all, do you have any questions about the exercise, about something? Okay. So today we are going to talk about hidden variables and about expectation maximization algorithm. So let's start. Till now, the general framework is that we have some samples, we have some observations, and we want to estimate the parameters of these observations. Now, till now, we dealt with simple or maybe a distribution that we can estimate their parameters easily. Well, what does it mean? So if we assume that our distribution is a Gaussian or is some exponential family that we can take, that we can compute the likelihood and take the maximum of the likelihood easily. But now let's assume that we want to measure the height of the population, and we got the samples, and the distribution looks like that. So it's something like that. Okay, this is a theta, and this is the probability. Now, what can we say about it? Now we want to estimate the parameters of this distribution. How can we do it? So now, in general, it's difficult. But let's suppose that I'm telling you that in the population there are men and women, and each one of them has a different distribution. So now I'm telling you that the distribution of men, it's this distribution, and the distribution of women, it's this distribution. Okay? So what you can tell me now about the distribution? Right, it's two Gaussian, and if I know exactly these two Gaussians, I can compute it. I know how to compute the likelihood for each one of them. So I can estimate, if I know that these two Gaussian, I can estimate the right parameters. Okay? Now, so in general, we say that we have hidden variables in this distribution. Okay, so let's formulate this a bit. So we have our examples, our samples that we see, x as before, and we have the parameters that we want to estimate, the parameters theta. But now I'm telling you that p of x given theta, okay, or log of it, it's very complicated. But I have some hidden variables, and these hidden variables, let's know them as z, hidden. Now, if you know z, it's easy. The distribution p of x and z given theta, it's easy to estimate the hidden the parameters. Is it clear? No. I will give more examples. Yeah, just so in this case, okay, in this case, what is z? Exactly, and as before, theta is the mean and the variance of the Gaussian. So in this case, we have theta is the two means of the two Gaussians and the two two variances. Yeah. Okay. So we have 4 parameters to estimate.
So in this case, there is no z.
If I'm telling you, no, there is z, but in general also. Okay. So in general, at the beginning, you don't know z, and when you are looking on this distribution of p of x given theta, it's very complex distribution. But when you know z, when you have the full data, it's become easy.
So the z is knowing what kind of distribution is it?
What?
Z here can be that I know that this is the distributions of height.
So just z is the I know that this sample came from the distribution of the women, or this sample came from men. So
They always will be discrete?
in this case, yeah. X is not discrete, but
so this is additional information I have on the distribution, but it's not a parameter I need to evaluate.
so just as it's not a parameter. No, it's just it will. Okay, so we will see that it will give you information. It will become easier to evaluate or to estimate the real parameters by knowing or guessing z. But we will see it. So in general, we have, you can think of it as we have z, and we sample some some example, some specific samples from it, and then we sample from the distribution x given theta and z. Okay, so we sample first of all from z given theta, and then we sample from x given theta and z. Okay, so again, we sample if it's a man or a woman, and then we sample the height of the man or the height of the woman. Okay. In general, if we can describe p of x given theta as a mixture of distributions. If these distributions are Gaussian, we call it mixture of Gaussian. So we can say that p of x given theta is equal to sum over all of the number of the Gaussians. If you have, in general, we can have k Gaussians. The distribution, the probability that of the specific Gaussian, of the k Gaussian, and times the probability of the Gaussian, mu k, sigma k. Okay, this is mixture of Gaussian.
The multiplication is multiplication of our probability, not of k, right?
Yes. Okay, so this is GMM. Okay, and it's also a mixture of distributions. We can think of it if we recording the activity of a neuron, and this neuron, we have 3 stimuli, and given some stimulus, the activity is distributed as Poisson with different parameters. So in general, if we don't know what is the stimulus, it's hard to estimate the parameters of this distribution. It's a complicated distribution. But if we know that, if we know the stimulus, it becomes Poisson, and we know how to compute the maximum likelihood. Okay.
This pi is not a multiplication, right? It's an amplitude of each.
Is a distribution. It's the probability to get the k Gaussian. Yes. Yes. So again, think of it. We first sample some z from the distribution, from this distribution. Okay. Here it's everything is given theta. Okay. So we first sample z from some distribution, and then we sample x from the distribution of x given z and theta. Okay, now if we have n hidden variables and n examples and observations, then p of xn given theta. So we know that this is because they are independent. Okay, the observation, we all the time assume that given theta they are independent, they are IID. So this we can decompose it to the multiplication of the xi given theta, right? As we did before. But the problem, what is this? What is this term? Right. We have also sum over k, or sum over all of our z. So this is, we have here summation over all the zi p of xi zi given theta. Okay? Now, what is the problem with this? What is the problem with this? Why we cannot, we know that this, we know that, we assume that this one is easy to compute the log likelihood of this one, right? Yeah, for example, it's Gaussian, or Poisson, or something like that. Right, we don't know, so this is gives us the summation. We don't know, so maybe I will clarify it. We have samples, and we don't know the hidden variables. So we need to marginalize it. We need to marginalize over all the possible z, because we don't know the real z. Okay, so this is the sum over z. But what is the problem? Right, I can't decompose it because, so the maximum likelihood in this case, the maximum likelihood estimator is argmax over theta of this term, of the log of this term. So this, because we have a log, it becomes the sum of over all the n as before, but we have inside the log, we have this sum. So sum over all the z p of xi zi given theta. And this is, it's hard to compute. It can be not convex, it can be very complicated function. We don't know how to maximize over it in general. Okay? So, because in the general case we don't know how to find the global maximum, the global optimum, we just can try only to get to local maximum of this function. So how can we do it? One possible way is to do gradient descent. What does it mean? Just if I have my likelihood function, and it can be very complex, very not non-convex. So I'm starting with some theta. I'm evaluate the likelihood in this theta, and then I'm calculate the gradient with respect to theta, and I'm going to the point that against the gradient direction. Okay, so for example, from this point, the gradient will be at this direction, and I'm doing it in iterations, and I will converge to this point. Okay, this is one possible way. For example, neural networks, when you're training your favorite neural network, you're doing this. You're using the gradient descent, but it's complicated because if you have a lot of parameters. You need to calculate the gradient for each one of them, and it can be very it's not efficient. But never mind, in neural networks there is algorithm that can do it in an efficient way. Yes.
So if you don't know the distribution, how can you compute the gradient?
I know it locally. I know, so here, right, for example, if I have only one, if theta is just one dimension, I can calculate here, right? I can calculate the likelihood here, right, and the likelihood here, and just I can take the empirical gradient, for example, just the difference between the two.
But you don't have the distribution, so how do you calculate that?
No, I can calculate the distribution. I don't know it in general, but locally I can know. If give me some theta, I can calculate the likelihood, but I can maximize it over it.
Do you mean maximize every z, then know the maximum of each?
No. Here is I don't have this here in this case. I have a complicated function. I don't care from all the z. I have examples. I can calculate the likelihood of the function, the likelihood of this, right? And just try to do my best. Just go locally for each step. Just go locally and try to maximize.
So it's kind of problem of instead of more complex function, then
yes.
just a problem of maximum.
Yes.
Okay.
Exactly. This is the problem. Okay. Now, another approach is just to say, okay, I don't know the hidden variables, but I know in general that there are some hidden variables in this complicated function. So let's try to estimate them. This is the general idea of the expectation maximization algorithm, the EM algorithm. So we have our assumptions here when we are doing EM. There are two assumptions. If you give me the full data, if you give me P of x and the hidden variables given theta, I can find the maximum of I can find the argmax of the likelihood. It's easy. It can be exponential family, and then we know how to find the maximum likelihood of it. But I don't have z, okay? But if I have z, I know how to find the maximum likelihood. The other assumption is that if I have theta, right here before I want to estimate theta, right? But I'm telling you, or my assumption is that if I have theta, I know how to evaluate the posterior of P of z given x and theta. Okay? I can evaluate this one, and then I can complete my my data. So we have here two problems. That if I have z, I can solve. I can find the maximum likelihood. If I have theta, I can complete my my data, and to get P of x and z. But I don't have each one of them. So what we can do basically, the general idea is, okay, just first of all just to guess one of them, and then start to iterate between them. Now I will explain, of course. This is the whole point of the EM algorithms. So just keep it in your mind that we have two hard problem if I don't know the z or theta, but if I know one of them, I can solve the other one. Okay, so as I said, we have two steps in the algorithm. First is the E step, or the expectation step, when we are maximize the expectation of the log likelihood, of the full log likelihood. What does it mean? So the E step, okay, I'm evaluate the expectation, we denote it as the Q function of theta and theta hat is sum over all the z, p of z given x and theta hat, log of p of x z given theta. Why this is the expectation? Expectation over what? Over? Right, over z given x and theta. Okay? So now let's assume that I have theta. We said before that our assumption is that it's easy to evaluate this term, right? If I have theta, I know how to evaluate how to complete my data, and then I can calculate this function. Okay? Now so the Q function, this function, what we really want to do is to evaluate the log of x given theta. This is our original goal, but we cannot do it. So we will try to maximize this function, and we will see that it will give us a good estimation for the likelihood of the full data. Okay, so this is the E step. We calculate the expectation of the log likelihood. And the M step, what is the M step? After we calculate the expectation of the log likelihood, what we need to do? What is the goal of our task? Right. So we have here that our new estimator, our new theta new is equal to arg max over all the possible theta of our expectation function of Q. Okay? Yes.
This is like given two parameters that I need to evaluate.
Right.
But I've access to only one of them, so I average over the other and then do maximum likelihood of the one that I need to know.
Yeah, you can think of it as, yeah, right. So now, okay, so now I have theta. What I can do, I can put it here, because I know that at the beginning I guess theta, right? I guess my theta hat, and then I calculate this function. This is how I begin. So now I have new theta hat, sorry, new estimator, and I can put it here and calculate this function again. And after I calculate this function again, I can put it again and take the argmax of it. And we will see that in each iteration I can only improve my likelihood function, the original likelihood function. So just to give you intuition, so this is the likelihood function. This is theta. This is the original likelihood function. And now, what I'm doing in the EM algorithm, I'm guessing some theta. Okay, let's call it theta all. I'm guessing some theta, and then evaluate the Q function. So, and the Q function is really nice function. It's convex because this is we know how to estimate. So now I'm telling you, or we will prove that the Q function is a lower bound of the real likelihood function, and so and it's tangent to the real likelihood function in theta hat. So this will be okay. So this will be, assume that it's convex, this function, maybe. Okay, so this is the likelihood function, and this is the Q function. Now, and here in theta head hold, they are at the same point, and they tangent to each other. Now, what I'm doing in the M step, I'm calculating the argmax of theta over my new function. Why I can do it? Because it's easy. We assume that it's easy. I have the full data. The function, it means that the function is convex, and it's easy to take the argmax of it.
Why does it mean the function is convex? Because we have the data?
I will not show it here, but basically because you just take expectation of something that you know how to, that it's also convex, that you know how to compute its max, its maximum. So it must be also. So now I'm taking the maximum of this, okay, and this, and here now I'm taking the argmax of it, and this it's theta hat u. Okay, and now what I can do, yes.
What's more, like the P of Z or the Q function?
The Q function. Now, now I can what I can do, I can calculate again Q, and I'm telling you, or you will prove that at this point the likelihood and my new Q are tangent to each other. So it looks something like that. Yeah, something like that. Okay? And now I can do again the same thing. Take the maximum of it and do it in iterations, and to converge to maximum, to local maximum. Okay, is it clear, the intuition? They must be the same only at the...
At the traces when Q function is on the ridge of increase, the L function also increase. That's why it takes the maximum and it pushes to...
Yeah, but yeah, we will show that now we will show that in each step you can only increase the likelihood, the original likelihood function, and we will do it by just evaluate exactly what is the distance between the real function, the Q function, and the real likelihood function. Okay, so to do it, to show that you can only improve the likelihood function, we need the following claim. So the claim one is that the Q function of theta and theta hat at time t plus the entropy of p z given x and theta hat t is not bigger than the log likelihood Ex given theta. P of z given x and theta hat at time t. And the equality holds for theta equal to theta hat t. Okay? So we can see here that we will prove that it's a lower bound, that Q function is a lower bound of the real likelihood function, and we can define exactly what is the distance between them if theta is equal to theta hat at time t. Okay? Because if it's equality here, then this term is exactly the difference between the two functions. Okay? Okay, so the entropy, we didn't define entropy. It's so the entropy. Not in this code. Okay, so no problem. So it's basically you can think of the entropy of z, p of z given x and theta hat is equal to sum over all the z, p of z given x and theta hat at time t log of p of z given x hat at time t. Okay.
We defined without the minus sign?
Yes, sorry. Sorry. It's the usual definition for entropy. Okay, So let's prove it. Question? Okay, so let's prove it. Q of theta and theta hat at time t is equal to what? By the definition, is equal to sum over all the z, p of z given x theta hat at time t log of p of x and z given theta. Okay, this is the definition. Now, okay, so now we can just we can decompose it to p of x given theta and p of z given x and theta, right? We just can if no, we can just decompose it inside the log. Just inside the log. So this is equal to sum over all the z, p of z given x and theta hat at time t log of p of x given theta, p of z given x and theta. Okay? I decompose this one. The log is over all this.
Sorry, we said before we cannot decompose it to the module.
No. You have here, no. We say that we cannot decompose p of x given theta. But if we decompose it to the sum, you have sum inside the log, and it's not there. But here I did different things. I just
No, we said about p of x and z can decompose them to the module.
I didn't. So here I just used the fact. That p of x given z, x and z given theta, or in general, p of x and y equal to p of x given y, p of y. Right? It's true every time. I can do it. So now, okay, so when you can look, this term, it doesn't depend on z. So we just can take it outside. And we have multiplication inside the log. So it's a summation outside. So this is equal to log of p of x given theta plus so it's equal to log of p of x given theta plus summation over the z, p of z given x theta hat log of p of z given x in theta. Okay? Right. So now here I can do the following trick, just to divide and multiplicate by log of by p of z given x and theta hat, and then I can decompose it to two terms, right? Because inside the log again I can decompose the multiplication. So I'm getting that it's equal to log of p of x given theta plus sum over all the z, p of z given x and theta and theta hat at time t log of p of z given x and theta divided by p of z given x and theta hat plus sum over z p of z given x and theta hat log of p of z given x and theta hat. Okay? If you don't understand some of the stages, it's in my notes. Now, what is this? This term is the likelihood. What is this term? Right, between? Right, x, right, z given x theta hat and z given x and theta. So we have a log of p of x given theta minus the DKL between p of z given x and theta hat and p of x z, sorry, right, z x and theta minus what is this term? Exactly the entropy of p of z given x and theta hat. Okay? So in general we got that q of theta and theta hat at time t plus the entropy of p of z given x and theta hat is equal to the likelihood log of the p of log of p of x given theta minus the DKL between p of z given x and theta hat and p of z given x and theta. Okay? Good. Now, in general, this term is positive or it's not negative. And then we got that the log likelihood is bigger than this term. And if we substitute theta equal to theta hat at time t, this DKL will become 0, and we'll get here that they are equal. Okay? So let's do a break and we'll continue after it. מה זה? ה-DKL הוא במינוס, כל ה-D הזה הוא חיובי.
נכון, אבל לייק זה פחות משהו, אז איך זה יכול להיות גדול ממנו?
כי תחשבי, לייק, מספר פחות משהו שווה למספר, זה ברור ש... זה היה טוב, אוקיי, כן, שאלה. זאת אומרת, זה by definition התוחלת על פי z. זה פשוט ההגדרה של תוחלת לפי z given x and theta. זה בדיוק כמו, זה ההגדרה. לפי p of x.
אני יודעת מה ההגדרה של התוחלת, אבל למה זה אמור להיות ערך כפול ההסתברות שלו? יש פה איזה ערך?
זה הערך. זה הערך.
כן, זה לא ההסתברות שלו.
לא, אז השאלה היא, זה בדיוק העניין, השאלה לפי מה את לוקחת את התוחלת. אם את לוקחת את התוחלת לפי, את לוקחת את התוחלת לפי משהו. אני לא יכול לקחת את התוחלת לפי זה, תחשבי שזה מספר, זה פונקציה.
זה ההסתברות שלו, אז אתה...
לא, אבל מה זה ההסתברות שלו?
של x ו-z,
של?
של x ו-z בהינתן θ.
לא. לא, אני צריך... אני בוחר ככה, זה הולך למשחק כזה. אני אומר לך לפי מה לקחת הסתברות, ואת לוקחת את אותו ערך שמופיע פה, ופשוט עוברת על כל הערכים האפשריים שההסתברות הזאת יכולה לתת, ואת שמה את הערך.
ההסתברות של הערכים האלה.
זה... לא, זה בדיוק זה. אם הייתי לוקח, אני יכול לקחת ה-expectation...
אתה לא יכול לקחת תוצאות של התרת נגדה ולעשות הסתברות לפי התרת קובייה.
לא, אני יכול, אבל אם זה לא תלוי אחד בשני, אז הם יהיו קונסטנט. זה בדיוק כמו שאת לוקחת expectation לפי איזשהו קונסטנט. מה זה אומר? מה זה בעצם אומר? זה אומר שאת לוקחת, שאת עושה sum over, נגיד אני לוקח פה על px. אז עוברת על כל הערכים האפשריים של x, px כפול c. אוקיי? שזה במקרה, זה בגלל שזה לא תלוי ב-c, יכול להיות שהיא c החוצה, ואז יש לך sum over all px. וזה שווה ל-1. אז אותו דבר, אני יכול, זה לא מעניין אותי מה הערך פה. בסדר? אם זה היה, עכשיו זה יכול להיות p של, לא יודע, c given x. זה יכול להיות כל דבר. אז אם זה c given x, אז אני עובר על כל הערכים, ושל x, p של x כפול c given x. זה מבלבל.
אני לא ראיתי את זה. אבל זה כאילו בתלוי קבועים פה, וזה דבר ששנה כל פעם, שנה את הערך הזה, בכלל? כלומר, על זה שישתנה?
כן, x... רגע. כן.
אותו תטא, אותו x, ובעצם כל פעם שנה את z, וזה שנה את הערך הזה?
כן.
אני אף פעם לא ראיתי תוחלת שהיא לא על ההסתברויות הרלוונטיות.
אבל זה כן על ההסתברויות הרלוונטיות, זה פשוט... ההסתברות שלה, יש פה את z. יש לך פה את z. זה לא קונסטנט, אם לא היה לך פה את z, יכלתי לשים את זה ככה. ואז זה מבחינתי c, ואז היה לך בסדר. נכון?
זה גם הסתברות של x.
לא, שנייה. אני משאיר... שנייה רגע, לא, שנייה. ככה בואי תסתכלי. זה expectation לפי z given x ותטא, נכון? עכשיו, זה אם לא היה לך פה z, אז זה היה מבחינתך איזשהו קבוע. נכון? ואז היה עובר. ואז היה בסדר, נכון?
גם לא.
או שלא?
כי זה תוחלת, כאילו זה... מה אתה תוחלת אם זה לא ההסתברות של הערכים שאתה...
אז זה בדיוק כמו לעשות תוחלת על מספר קבוע.
מה אתה?
לא, אבל זה בדיוק העניין. אין פה, מה זה מה הטעם? השאלה היא, את יכולה בעיקרון להראות על זה הרבה דברים יפים, אבל אחד הדברים שזה קונבקסי. זה הפונקציה הזאת, עזבי רגע...
אבל למה לעשות את זה בכלל?
למה לעשות את זה? זה בדיוק מה שזה. זה בדיוק מה שאנחנו מוכיחים. אנחנו מוכיחים שאם את עושה את האלגוריתם הזה, את מחשבת את הדבר הזה, הפונקציה הזאת היא גם lower bound על ה-likelihood האמיתי, כן? היא גם lower bound על ה-likelihood האמיתי, וגם היא שווה ל-likelihood במקסימום שלה.
מה הקשר? סתם, כאילו, זה סתם כזאת של הסתברויות שהן לא קשורות אחת לשנייה, למה לעשות את זה?
אז זה בדיוק בעל של זה.
למה אתם רוצים לחשוב?
זה שאלה אחרת, אבל...
אתה גם לא מתחשב בכל הסתברויות שם, אתה לא יכול להביא תוחלת שלה.
תוחלת שמה. זו הגדרה של תוחלת. אני לא חייב. אני לא חייב, מחקתי את זה. תניחי שמישהו חשב בשבילך על פונקציה, ועכשיו אנחנו רוצים, למה הוא חשב על זה? אפשר להראות את זה. אם תסתכלי בזה אחרים, אז בעצם אתה רוצה להראות בעצם שאתה צריך בעצם פונקציה שהיא בעצם סכום של לוגים. ואת יכולה להראות שהדבר הזה ממזער בעצם את ה-L2 square בכל שלב בעצם בין ה-likelihood לזה, אבל בגלל זה אני לא רוצה להיכנס לזה. הדבר העיקרי הוא שיש איזושהי פונקציה, הפונקציה הזאת, ויש לה תכונות שהן טובות לנו. אז את לא חייבת, אנחנו לא תשימי לב, אני לא השתמשתי פה בעובדה שזה תוחלת בשום שלב. פונקציה. את לא חייבת לקרוא לתוחלת אם את לא מרגישה נוח עם זה. אוקיי? אל תקראי לזה תוחלת אם את לא מרגישה נוח עם סוג כזה של תוחלות. פשוט פונקציה שיש לה תכונות שאנחנו מראים שכל פעם שאתה לוקח את המקסימום שלה, אתה עושה את האלגוריתם הזה, אתה בעצם ממקסם את ה-likelihood. כן. אנטרופיה? אנטרופיה זה... מה למדת? אוקיי. אז אנטרופיה זה... אפשר לחשוב על זה בתור מידת האי סדר במערכת. זה... לא ראיתם את זה אף פעם בשום קורס?
אני ראיתי את זה בקורס תואר.
וואלה.
למדתי את זה בתור מדד לאי ודאות.
כן, זה מדד לאי הסדר או מדד לאי הוודאות במערכת שלך. זה קצת יותר מסובך להראות את זה, אבל קונספטואלית אתה יכול לחשוב על זה, כן, בתור כמה בטוח אתה אם יש לך, נגיד אם יש לך פונקציה, כן, ואם זה דלטה פונקשן, אז האנטרופיה שלך תלך לאפס. אם יש לך פונקציה שהיא אחידה על פני הזה, האנטרופיה שלך תלך לאינסוף. בעצם אתה תקבל מקסימום אנטרופיה. זה בעצם כמה הפונקציה עצמה, כן, אפשר לעשות את זה כמה היא דטרמיניסטית. כמה אתה קרוב להיות דטרמיניסטי, כמה אני דוגם, במובן של אני דוגם משהו מהדיסטריביושן הזה, כמה אני יכול להגיד לפני זה, מה אני יכול להגיד על הדיסטריביושן הזה, כמה אני יכול להיות בטוח מה יצא לי.
פה זה 100%, אני תמיד יודעת שיצא תורה.
מה זה? לא, פה הפוך, פה אתה לא יודע.
למה? כי כל איקס שתדגום לי, אני יודע איזה איך זה יהיה.
לא, זה הפוך, אתה דוגם, לא.
אתה דוגם Y?
לא, מה זאת אומרת? אתה דוגם, אוקיי, אולי לא זה. כשאני מדבר שיש לך דלטה פונקשן, אתה תמיד תחזיר את ה-X הזה. אוקיי?
אם אני כאילו עושה אינטגרל או מה?
לא, אתה דוגם, יש לך דלטה פונקשן, ואתה דוגם מתוך דלטה פונקשן, אתה דוגם X מתוך דלטה פונקשן. בסדר?
אוקיי, כלומר מתוך כל הערכים פה.
כן, מתוך כל הערכים פה אתה דוגם איזשהו X, אתה תמיד תדגום את ה-X הזה. זה by definition.
זה כאילו ההסתברות, אתה רוצה להגיד?
כן, יש לך...
ההסתברות שאני אקבל כאילו כוח על ה-X?
כן, יש לך גאוסיאן. בואו נתחיל מגאוסיאן, בסדר? בואו נתחיל מגאוסיאן. אז ההסתברות שאני אקבל X פה היא יותר קטנה מההסתברות שאני אקבל X פה.
כלומר, לדגום X, זה לא...
כן, זה ה-PDF. אוקיי? בסדר? עכשיו, אז פה הוודאות שלי היא מלאה. אני תמיד אקבל את אותו X. ופה, בדיוק, ופה אני בעצם אקבל אנטרופיה גבוהה מאוד, כי אני לא יודע להגיד לי שום דבר, אין לי שום X מועדף. יש לי אי ודאות מאוד גדולה במערכת. עכשיו באיזושהי מערכת, ואתה בעצם רוצה, היא נותנת לך איזשהם סאמפלים, ואתה רוצה לנסות לחזות את הסאמפלים, מה היא נותנת לך, אז יש אנטרופיה גדולה, אתה לא יכול זה. יש לך המון אי ודאות. זו האינטואיציה. זה גודל שמאוד נוח. מה זה?
ובתוך המשוואה שסתרת אי אפשר לקרוא.
לא. זה גודל מאוד נוח, כן? זה גודל מאוד נוח, הוא חיובי, הוא מתקשר לנו ל-DKL בכל מיני צורות, לאינפורמציה שעוד מעט נדבר, שכבר שיעור הבא נתחיל לדבר על זה. אבל כן, זהו, זו ההגדרה שלו. כן. אני רק אגיד עוד משהו, סליחה. אתה יכול להראות על זה כל מיני חסמים שמאוד נוח לעבוד איתם.
כמה אי ודאות אני יכול לקבל?
חסמים על, קודם כל אתה יודע שזה קונבקסי ודברים כאלה, אתה יכול להעריך כמה אתה רחוק כן.
ה-EM ביחס לגרדיאנט דיסנט, עבור אותו תנאי התחלה אנחנו מתכוונים להגיע לאותה נקודת מקסימום.
נכון, אבל הבעיה שגרדיאנט דיסנט, הבעיה שאתה מתחיל לדבר על computational time, computational effort, אז אתה בעצם בגרדיאנט דיסנט, תחשוב, אתה צריך, אם יש לך המון פרמטרים, אז אתה צריך לשערך עכשיו ברשת נוירונית. אתה מכיר רשתות? אוקיי, לא משנה. במשהו, אם יש לך מה. כן. כן, עד כדי בלתי אפשרי. כאילו... ל-EM יותר קל, כן. כי אתה בעצם, אתה לא לוקח את הנגזרת של כל תטא. אתה רק מחשב בעצם... אתה מחשב בעצם את המקסימום על פני פונקציה הרבה יותר פשוטה. כאן בגרדיאנט דיסנט אתה תמיד הולך צעד נורא קטן. צעדים שלך נורא קטנים. באופן אינפיניטסימלי קטן.
ואם אני יכול לחשב את הלייטינג פונקשן גם את הגרדיאנט שלנו, ואז אני עושה גרדיאנט.
עדיין זה נכון רק ללוקלית. עדיין צריך איזה לוקלית. אם אתה יודע לחשב ביעילות את הגרדיאנטים, אז כן. אז אתה תהיה... תלוי מתי. יש כל מיני חסמים על קצבי התכנסות, גם על ה-EM, יש חסמים על כמה מהר אתה מתכנס. אבל זה משתנה, יש מקרים שזה יעבוד יותר מהר, יש מקרים שזה יעבוד יותר מהר. אבל בעיקרון כן, אתה תגיע לאותו מינימום, תתחיל באותו מקום.
אז איך אני יכול עבור בעיה ספציפית, איך אפשר להשוות על ההערכה למי יתכנס יותר טוב, מי יתכנס יותר מהר?
בדרך כלל אתה לא, יש לך משפחות של דברים. בדרך כלל אם יש לך, EM זה משהו שאתה בעצם צריך, אתה בעצם צריך הרבה, אתה צריך כאילו הרבה, זה משהו שאם אתה יכול, אוקיי, נגיד את זה ככה, אם אתה יכול לחשב את הגרדיאנט דיסנט ביעילות, כן? את הגרדיאנט שלך, כן, ביעילות, אתה כנראה תעדיף, אתה ברוב הפעמים תעדיף גרדיאנט דיסנט לעשות. זה יביא אותך יותר טוב, נגיד, יותר במהירות יותר טובה על זה.
אוקיי, מה הכוונה ביעילות פה?
מבחינת זמן ריצה. דיוק הזה תמיד יתכנס לאותו מקסימום, אם אתה מתחיל באותו מקום.
אוקיי, ואם אני לא יכול לחשב את זה, אבל אני לעשות בנומרי, finite difference וכאלה, אז ה-EM מתכנס באופן יותר טוב?
אז תלוי מה, בדרך כלל אני חושב שהרבה מאוד, שרוב הפעם משתמשים ב-EM, אני חושב. למה בדיוק זאת שאלה, אבל לדעתי הוא יתכנס לך יותר מהר. נומרית אני חושב שיתכנס לך יותר מהר.
יש עוד שאלה לא קשורה לזה.
כן.
דיברנו על פישר אינפורמציה וכל דברים האלה.
כן.
כמה אני יכול להעריך את הפרמטר.
כן. נראה לי.
מידע בהתפלגויות שמתכנסות לדברים גאוסיים.
לא, דיברנו על פישר אינפורמציה בכלליות והראינו דוגמה על...
כן, אבל זה נכון בעצם לכל מדידה שאני עושה ואני רוצה להעריך משהו שבסוף מתפלג גאוסי.
אוקיי.
כאילו שהסנטר לימיט עובד ואני דברים נהיים גאוסי. אבל אם יש לי משהו שזה לא קורה...
לא, יש לך... הפישר אינפורמציה, דיברנו על זה שהפישר... הפישר אינפורמציה נגדרנו אותו באופן כללי. לא, בלי קשר לגאוס.
לא, אבל הוא מסתמך על הסנטר לימיט כיוון שאנחנו בממצאים האלה הופכים נהיים גאוסים בהתפלגות שהדרך ממוצע נהיה גאוסי.
אבל, לא, רגע, שנייה. זה שני דברים אוקיי, זה שני דברים שונים. אתה אומר, ה-feature information אומר לך הדבר האופטימלי ביותר שאתה יכול לעשות. הדבר האופטימלי ביותר שאתה יכול לעשות זה אם אתה לוקח אין סוף דוגמאות וזה. אתה מדבר פה, אוקיי, יש לי עכשיו משהו, אני רוצה לחשב עבור הדבר הזה באופן ספציפי כמה הוא טוב, נכון? מה ה-feature information שלו, כאילו, מה זה, נכון? זה מה שאתה מתכוון, שיש לי איזשהו מספר דוגמאות סופי. שלא הבנתי אותך. אני חושב שצריך להתחיל בכל מקרה. אז אחרי זה. אנחנו רוצים להתחיל? כן. נכון, אני הייתי לך, סבבה, קיבלתי, אתה צודק.
לא רציתי לסמוך עליי.
כמו שתמיד שאתה נוסע איתי באוטו?
Okay, so before the break we saw the following lemma. We saw that q of theta and theta hat at time t plus the entropy of p of z given x and theta hat at time t is not bigger than the likelihood log of p of x given theta. Okay? And if theta is equal to theta hat, we have here equality. Okay, now we want to prove that in each step the likelihood function can only increase. Our estimation for theta can only increase the likelihood function. What does it mean? So if the likelihood function, the log likelihood, is, let's denote it as L. Okay, this is p of x given theta. We want to prove that L of theta hat at time t can be only smaller or equal to L of theta hat at time t plus 1. Okay, this will tell us that in each iteration of the maximum of the EM algorithm, we can only improve the estimator. Is it clear why? Good. Now, so this is what we want to prove, claim. Now let's prove it.
Sorry, I'm just confused about the notation. I theta.
It's L, small L. Sorry. Okay. Now, so we know that the theta hat at time t plus 1 is equal to what? How we choose theta hat at t plus 1? argmax, exactly, argmax over theta of our q function. Okay, so it's q of theta hat, theta and theta hat at time t. Okay, now that means that for every theta, it holds that q of theta hat at time t plus 1 and theta hat at time t is bigger than theta q at time of theta and theta hat at time t. This is by definition. If we're taking the maximum over q, over theta of q, so at time t plus 1, we will have maximum. Is it clear?
It's not supposed to be theta hat t, right?
Here it's
Next to the theta.
this is theta hat t plus 1, this is theta hat t. Okay? We're taking just the maximum, so it's bigger than any theta. Now,
Not supposed to be with theta in time t.
here you have theta for every theta. Here it's theta, it's not theta hat.
And why is there not?
Here, because I chose particular theta. I chose the theta that is maximum. This is how I chose theta t plus 1. Okay, so now, and in particular, if I'm choosing theta is equal to theta hat at time t, this is also, it holds, right? Because it holds for everything. Now, we saw before the claim that we proved before that that q of theta hat at time t and theta hat at time t is equal to the likelihood function of theta hat at time t minus the entropy of z given x and theta at time t. Okay? Right? You saw it?
Without the hat.
Without? No, but we saw it in, no. We saw that in general there is it's smaller, but when we have the theta hat is equal to that, the DKL is equal to 0 and there is equality. So so in general, so we saw that q of theta hat at time t plus 1 and theta hat at time t is equal to the likelihood of theta hat at time t plus 1 minus the DKL between p of z given x and theta hat at time t and p of z given x and theta hat at time t plus 1 minus the entropy of p of z given x and theta hat at time t. Okay? So if we combine these two arguments, okay, if we substitute here, we will get so we'll get that it's q of theta hat at time t plus 1 and q and theta hat, sorry, at time t, right, is bigger than q of theta hat at time t and theta hat at time t, and if we'll put this and this, we will get that the likelihood of theta hat at time t plus 1 minus the likelihood of theta hat at time t is bigger than the DKL, this DKL. The DKL between P of z given x and theta hat at time t and P of z given x and theta hat at time t plus 1. And because this is a positive term, we can only improve this is bigger than 0, and we can only improve for each iteration, we can only improve the likelihood function. Okay? Is it clear? It's nice because it tells you how much you improve in each step. How much I will improve in each step by the DKL, by the difference between z given x and theta hat at time t and z given x and theta hat at time t plus 1. You can think of it as how much I improve my estimation for z given x and theta. Okay, how much I improve the estimation, how much the likelihood will improve is how much I improve my estimation of z given x and theta.
You don't know that. DKL you don't know. You cannot calculate.
No, in general, no. Okay, so we saw that we can only improve the likelihood, and in the exercise you need also to show that it's a fixed point, that the fixed points of the EM are also stationary points of the likelihood, because we improve in each step the likelihood, right? But maybe the maximum of the fixed point of the EM are not the stationary points of the likelihood, and then we will not get to the maximum. Okay, good.
But if we only improve, then if there's a maximum,
You can stuck in some point, but it's not it's not a local maximum of the likelihood. For example, if you have a function and you improve in each step you improve the function, okay? But if it's not, here you have the Q function, but if the stationary points of the likelihood are not the fixed points of the EM, you can just go, for example, I will go here and will stack at this at the maximum of the Q function, but it's not the stationary points of the likelihood. It's not the maximum, the local maximum of the likelihood. I will stuck here and not here.
so you also have to show that it's the only fixed point.
No, it's not the only fixed point. I can stack. Okay, so I can stack in a local maximum of the likelihood. Okay, in general the likelihood is not convex. I have many fixed points, many stationary points, and I can stack in each one of them. It depends where I started. But if Yeah, but if I don't, if the fixed point, if the fixed points of the Q functions are not the stationary points of the likelihood function, I will get to a fixed point in the Q function, but it will not be even a local minima or maxima. Sorry, a local maxima of the likelihood. It just be some point in the likelihood, not a maximum. Is it clear?
Okay, but you have to show that the maximum is the fixed point, but that there are no other fixed points.
No, but there are many fixed points in the likelihood.
So even if the maximum is a fixed point, you can still get stuck on the way to it.
Yeah. Because it's local. I will stuck here. I will not go to here.
So what's the point of showing that it's a fixed point?
It's because EM promising you that you will converge to a local maxima, just local, not global. You don't have any guarantee that it will be global. This is the best that you can do. In general, in non-convex functions, it's the best that we can do without assuming something. If I don't assume anything, it's the best I can do. Converge to a local optima.
And if we did achieve the local minima,
Yeah.
can we imply anything about the likelihood?
About the global?
Yeah.
So you need to assume something. For example, in general, no, it's meaningless. Yeah. In general, so you can think of you can solve it by a random initialization. For example.
We won't know that we achieved the global maximum.
Right. So you can choose, I don't know, choose a million different starting points, and then converge in each one of them and just take the maximum. Okay? You can show, there are some works that show that if you have a lot of parameters, then you have a lot of local minima, but they are pretty much the same. For example, in neural networks, there are some works that show that although that we have a lot, we have millions on millions of parameters of ways, and we can stack in a lot of local minima, actually all the local minima are the same, or pretty much the same, and it doesn't matter where we started. But you need to assume something, or you need to show it numerically.
Yeah, but over there we just care about the loss function. So we just want to know that our local maximum or minimum is close enough to the global maximum.
Right.
Here, if the local maximum, the value of the local maximum is very close to the global maximum, so if you have two peaks,
yeah,
and the value, the likelihood value is very close to each other, still the parameters might be very far away.
You're right.
So in neural network, it means something. If you get the local maximum, you are close to the loss function with high probability. But here, even if you are very close to the global maximum in the value, in the y-axis, it means nothing about the x-axis.
You're right. You're right.
Does it mean anything?
No, in general, no.
Okay.
Questions? Yes.
Also for the general logic, it's like if you know this Smith constant and you know that there's two parameters, why instead of which still want to find the theta that is a single parameter to approach the whole function?
Again?
Like at the beginning we thought about there is two population of the Smith constant, and we know that there are sampling from different groups. And finally what we are doing is that by assuming we know what is the structure of this thing, we still get the maximum likelihood of gap is beta given x given beta. But this is as a single parameter. I mean that why it is still meaningful, why we're interested know we currently have, what is it actually?
No, no. So okay, so in the case of the two of the population, we have four parameters.
Yes.
It's not only the mean. It's not only one parameter. It's the mean of each one of the distribution.
Yes.
So we are interested in general. We want to describe. I don't care from. I want to describe the distribution, the full distribution, the best as I can. Okay, I want theta, or it can be a vector of thetas that will describe me the best that you can think of it as if I'm sampling from this my distribution. I will get the most accurate samples. Okay, I want to describe it the best. So in general, I don't. If you have a good solution, how to evaluate, how to estimate theta that it doesn't depend on the x, it's okay. But in general you can't, and it's easier to evaluate to split theta to theta of z1 and theta of z2 and theta of z3, and just to evaluate them separately. Is it answered your question? No.
Because I assume that you can never do better for just get a single distribution if you already know that it is a mixture of two Gaussians rather than just doing with two Gaussians separately.
But no.
There are two estimates.
Okay. So okay. So no, but I don't know. I don't know the what are the points. What are the Gaussians? It's the same problem. I don't know what are the points of the Gaussian. What each of the points, what Gaussian is belong to. Okay. I don't have. So I have the distribution. I don't have this one. I don't have it. Even though okay, maybe it will be simpler like that. If I know, if you tell me what points are from which of the Gaussian, for each point what is the Gaussian of it that it came from, then you're right. I can evaluate this Gaussian. I can evaluate exactly this Gaussian, and then just to look on the maximum of the likelihood of each one of them. But in general, I don't know it. So when I'm guessing it, there is no promising that I will converge to the right solution. Okay? In random solution, I don't know how to evaluate if it's this Gaussian or this Gaussian. I will converge to something that is close, or that is local maxima of it. That's it. Okay? Question? Okay, so now we saw that it's a good. So this algorithm, this Q's function, is good in the sense that it will bring us to local minima of the maxima, of the likelihood function. Now let's see the M for exponential families. So in exponential family, we can describe it as log of p of x and z given theta is equal to sum over j between 1 to m, a j x and z times b j that depends only on theta plus c of x and z plus d that depends only on theta. This is a general form of exponential families. All the distributions, most of the distributions that we saw till now are from exponential family. So if I am assuming, look, this is the full data, okay? It's given after I know z. For example, it can be, if it's Gaussian, so we have here mixture of Gaussians, okay? Now, in this case of exponential family, the Q function is Q of theta and theta hat at time t, okay? By definition is equal to sum over all the z, P of z given x and theta hat at time t, log of P of x and z given theta. This is definition. And now if we substitute this, we will get that it's equal to sum over all the z, P of z given x and theta hat at time t, sum over all the j between 1 to m, aj of x and z, bj that depends only on theta, plus c that depends on x and z, plus d that depends on theta. Now, we can decompose it to, look, this is, this term b doesn't depend on z, okay? And also d doesn't depend on z, so we're left with only a and b, and c, sorry. So we have that this is equal to sum over j between 1 to m, the expected value according to P of z given x and theta hat at time t of aj of x and z, okay, times, this is outside the expectation, b is outside the expectation, bj of theta, plus the expectation according to P of z given x and theta hat of c of xz plus d of theta. Okay? Now, what is nice here, that this is, so d it doesn't depend on theta hat, right, and z, so we can evaluate d and b, we can evaluate only one at the beginning. For every theta I can evaluate b and d, and this one, it doesn't depend on theta. Okay? It doesn't depend on, it doesn't, when I'm taking this, because it doesn't depend on theta, I don't need to take it into account. So, actually, what I really have is just take the maximum over this term. And you will see next week that this is the sufficient, it's called the sufficient statistics. Of the distribution. Okay, so just keep it in your mind that for exponential families, it's easy to compute. It's easy to evaluate or to find the right to find a solution for the EM. It's easier than in general distribution. Okay. Questions? Now, so till now we saw question?
And so, no, I was just wondering, you also need D, but you maximize over theta h, right? So you don't need D.
Right, you don't need, exactly.
Yeah, you don't.
Yeah, you don't. Okay, so till now we saw what happened, what is Q in the case we have only one, when we have only one X. Okay, we have only one observation. But now let's assume that I have IID multiple observations. So I have multiple observation, and I have Z1 to Zn and X1 to Xn. Okay?
The same n?
What?
Same n?
Yeah. It's so no, it's okay. It's I mean what is, so let's do it. I mean, what is the Z that sample in the n example? This is what I mean. So the Q function is theta and theta at time t of sum over all the Zn, P of Zn given Xn, theta hat t log P of Xn given, Xn Zn given theta. This is in general. Now we'll try to make it more simple. Okay, so first of all, let's go over all and let's clarify some notations. If I have, so if I have Z1 to Zn, it's a sequence of random variables.
Can you explain again what's the meaning of, what exactly the problem here?
Zn, what?
I mean, what's the difference between this and the previous example?
Now you have multiple observations. Okay, you have here Zn and Xn. It's all your observations. It's n observations.
And the sum over Zn.
You need to sum. Okay, so I just want to clarify the notation. So I think it will be more clear in a moment. Okay. So if I have Z1 to Zn, it's a sequence of random variables with some joint distribution. So here I have P of Z1 equal to, capital Z1 is equal to small z1, Z2 is equal to some Z2, till Zn is equal to Zn. Okay? I have some, for each random variable, I have some observation, some values. Okay? For each examples, for each samples, I have some value of Z. So this is a distribution, and we denote Zn as the random variable, the sequence of random variables Z1 to Zn, and small zn, lowercase zn, is equal to a specific value, specific n values, z1 to zn, that we assign to each one of the random variables.
The sum there is it on capital Z or?
No, it's small z. I'm going over all the values, all the possible values. Okay? And therefore, P of, so this is equal to, we also denote it as P of Z1 to P of Zn. Here it's lowercase, Z are the values of Z. And we can also say P of Zn. This is what we mean when we are saying Zn. That each one of the components, each one of the random variables, gets a specific value of Z. This is a lowercase. This is lowercase. It's a value, a specific value, Zn.
But it's also the lowercase.
This is lowercase, right? This is specific value. Sorry about the notation. This is lowercase. This is specific values. Specific values, specific n values for each one of the random variables.
Yeah, so the other one is supposed to be uppercase.
No, it's a lowercase.
Can you denote them?
Yeah, sorry. Okay, so yeah, okay, so it's not
Maybe a different letter.
with what?
With a different letter, maybe.
Okay, you know what? Let's denote it with a different letter. Okay, let's denote it with I don't know, G. Okay. Gn, G2, G. G, P of G. Okay.
In the bottom line, it should be.
So here it's G.
Yeah, but Zn n should be on the top. The top.
An upper index here.
Yeah, upper index.
Where?
Exactly what you said.
Here.
It should be Gn when the n is
right.
uppercase. Upper.
Yeah, right. You're right.
Super
Exactly.
yeah.
And the sum is over Gn.
And the sum here is over Gn. Right. Exactly.
So
And here it's Gn. Okay.
So some GK that takes the same values from 1 to K.
Exa-
To M or something like that.
It's all the values that all the n random, the n hidden variables can get.
So if it's two Gaussians, then it's only 1 or 2.
Two.
This Gaussian or that Gaussian.
Yeah. If you have the yeah. Okay. Now, when we say the marginal distribution, so P of Zi is equal to J, okay? It's just summation over J1 till summation over Ji minus 1, summation over Ji plus 1 of till summation over Jn P of J1 Jn. Okay? We are marginalized over all the components that are not the I component. Okay, this is always true, and we can also say that we can change it to P of Jn. Okay, it's the same, just notation. Now when we want to take the expectation with respect to all the Zn for a function that depends only on the I component of Z, that means I'm taking the expectation of GI, no GI, Fi of